So, Hello everyone. I'm Gitanjali. I'm a PhD scholar from IIT Delhi, and I'm the TA for this course, which is Foundation of Classical Electrodynamics. So, in previous class, we have looked what is how we can solve the potential of a system using separation of variable whenever the reason satisfies the Laplacian equation. So, and besides that, we have also seen how to calculate the electric field for a polarized object or for a dielectric medium using surface bound charge or the volume bound charges. So, in today's session, we'll go through another trick to find out the find out the electric field or the potential using the method of images. So this is one of the trick that you can use for a simplest configuration. So whenever you thought that you can use the method of images, then you can use this using the image charges by replacing by using image charges as well as real charges. Then you can go on to calculate what is the potential. Then from potential you can calculate surface charge density, electric field, force, and work done. So we'll see that we'll see few problems related to this concept, as well as we'll start looking at problems of magnetostatics. So like electrostatics, where we have seen the source charge is at rest. So based on that, we saw that we can write the electric field in terms of gradient of some scalar potential, and the curl of electric field is zero for the electrostatic case. So similarly, here we have in magnetostatic, we'll deal with the steady current, so which doesn't change with time. So because of that, and the condition for magnetostatics to happen is the divergence of J should be zero, and the Ampere's law should hold. So Ampere's law, it's like the Gauss law for the magnetostatic. So in electrostatic, you have seen E dot ds is integration of E dot ds is Q enclosed by epsilon naught. Similarly, here we have B dot dl is mu naught I enclosed. So these are the similarity between electrostatics and magnetostatics. And besides that, you can also use Biot-Savart's law, which is a general formulation to find out the electric field or for any type of current distribution. But whenever you have symmetry, you can use the Ampere's law. So we'll see problems related to magnetostatics as well as the method of images. So let us see our first problem. We'll start solving easy question first, then we'll move towards the difficult questions. So first question is based on the method of images. So there are two charges Q and 2Q which are placed along the x-axis, and it is placed in front of a grounded conducting plane. So they were located respectively at a distance of 0.5 meter and 1.5 meter from the plane. So we need to calculate what is the force acting on the charge Q for this configuration. Four option is given, and the only difference is here the coefficient is 1 q square by 8 epsilon naught, 5 q square by 8 epsilon naught, 3q square by 8 epsilon naught, or 7q square by 8 epsilon naught. So, so you can easily see you can use the method of images to solve this problem. So here we have a grounded conducting plane, and there are two charges placed along the x-axis. One is q, another one is 2q. So this is at a distance of 0.5 meter, and 2q is at the distance of 1.5 meter. And the trick is to replace the conducting plane by the image charges and the real charges. 2q, here 2q, here we will have minus q and minus 2q. So the distance from the plane where the grounded plane is there, so the distance should be similar, should be equal. It should be 0.5. This is 0.5. This is 1.5. So this would be 1.5. So this configuration satisfies the boundary condition. That is why we say that we can use this formulation to find out the force. So, okay, one of you have already solved it. So let me quickly solve it, then let me see whether your answer is correct or not. So force on charge Q should be due to the force due to 2Q minus Q and minus 2Q. So this will be 2Q minus Q and minus 2Q. So force is based on the Coulomb's law. So 2Q square 4 pi epsilon naught. Distance between them is 1 meter. Minus q is the distance is also 1 meter. So this is minus q square 4 pi epsilon naught 1 square minus 2q square. Distance from this to this would be 2 square. So this will give q square by 4 pi epsilon naught, and here we have q square by 8 pi epsilon, which will give q square by 8 pi epsilon naught. So answer is, you are correct. Answer will be option A. Okay. So next question. Let me read out the question. There is a point charge which is placed between two semi-infinite conducting plates which are inclined at an angle theta such that a total of 23 image charges are formed. What is the value of angle theta? So you have two rounded conducting plane and the angle is theta. And there is a charge here, and it is saying there are 22, a total of 23 image charges are there. So you need to find out the theta. Anyone recall what will be the formula to be used for this case? To n minus 1. Okay, let me see. So what do you mean by n then? The angle. To pi by n minus 1. Yes, you are correct. So the formula is to use 2n minus 2 pi by n minus 2 pi by theta to be accurate, 2 pi by theta minus 1. So for any angle theta, the number of image charges, it will be find out by using 2 pi by theta minus 1. It should be equal to the number of image charges, which is given 23. So That means 2 pi by theta is 24. So theta is 2 pi by 24. And if you calculate it, it will be pi by 6, which is, sorry, pi by 12. This will give an angle of 15 degree. Okay. Let us move to our next problem. So there is a charge Q placed in an open grounded conducting parallelepiped at ABC, where ABC are opposite. So, sorry, ABC are positive. Using the method of images, you need to find out what will be the electric potential in a region of the charge Q for which x is greater than 0, y is greater than 0, and z is greater than 0. Anyone can let me know what will be the total number of image charges here? Yes, there would be 7 image charges here because if you see for a angle, the angle between this plane is 90 degree. For a 90-degree angle, you will have 3 image charges. So for this plane, you will have 3 image charges, and if for this two plane, this and this, you will have 3 image charges. But one of these image charges will be we already have considered for this plane. So total 2 will be there, and for this two plane, sorry, for this two plane will have 3 more, but one of will be common. So that is why 2 will be there. So total will be 7 image charges. So total image charge is 7. Now let us find out the location. So 1 will be minus q at A, B, minus C. So let me draw it. Q is here. So this is A, B, C. So 1 will be here minus q at A, B, minus C. And other will be here, which is A minus B, C. Other will be here, which is A, sorry, minus A, B, C, minus A, B, C. And other image charges is opposite to ABC, which is minus A, minus B, minus. This is 3, and 4 more will be there, which is Q at minus A, minus B, C, and minus q at minus A, B, minus C, and 1 is A, minus B, minus C. So we know the coordinates now. So potential would be Vx, y, z, 1 by 4 pi epsilon naught q square root x minus a square, y minus b square, z minus c square square root x, this one minus a square y minus b square plus, sorry, I'm considering plus q, right? So let us take this one. So x plus a, y plus b, z minus c square, and q square root x plus c square, and y minus b square, z plus c square, this one, plus q square root x minus c square, y plus b square, plus z minus plus c square. Other part is for minus q, which will be q square root x minus a, y minus b, z plus c square. So minus q square root x minus a square, y plus b square, z plus c square, minus q x plus a, y minus b, z minus c square, and minus q. Last one is x plus a, y plus b, and z plus. This is the potential. Okay. So let us see the fourth question. Fourth question is quite easier one. So there are two forces there. One is electric field, one is magnetic field. You just need to find out the total force. So a proton travels through a uniform magnetic and electric field. Magnetic field is given. It is B is a y cap, and A is a constant, positive constant. If at if at one moment the velocity of the proton v, it is v z cap, where b is positive. What is the force acting on the proton if the electric field is minus c x cap? So we'll have both electric and magnetic force. So this will give the magnetic force, this will give the electric force. So force will be q e plus v cross b. Q is cx cap plus p cross b will give ab. Y cap, z cap cross y cap, it will give minus x cap. So that means this is minus q x cap c plus ab. Okay. Third problem at the end. You mean this one? I think the image charge is clear to you. It's 7 charges. So uh, can you let me know in which part you have the doubt, whether it is finding out the image charges or finding out the potential? You mean to clarify from here or here? Calculating the potential part. So if you know the coordinates, then it's quite easier to find out the, okay. So let me, so image charge finding is, I think it's fine for both of you. If not, let me say once again. So there are uh, three planes which are at 90-degree angle to each other. So total number of combination of two planes will be three, right? One is you can consider this plane or this two plane or this two plane, right? So there are three, let's say I should one, two, three. So that means one of the one, two plane is at right angle, two, three plane is at right angle, and 1, 3 plane is at right angle. And we have seen for each right angle, you will have three image charges. So 1, 2 will give three image charges, right? Let us see 1, 3. 1, 3 will also give three image charges, but if you see one charge, these two plane will share one charge, one image charge. That is why there will be two. And for 1, 3 also, sorry, 2, 3 also, it will be 2. So it's like uh, there is one image charge will be here for 1, 2, one will be here, and one will be at a point which will be shared by 1, 3. So, so that is the charge which is given. Charge Q is given. It is at ABC point. Yes, it is given in the question. So to find out the now to find out the location, what you need to do. So Q is present at A, B, C. So that means one image charge will be there at minus Q, which is at minus A, minus B, minus C. Right? So this is trivial. To find out other image charges, what you need to do. So you need to look for the planes. So if you consider the second plane here, so Q is at A, B, C. So that means in the bottom we'll have minus Q at A, B, minus C. So that is why minus Q will be there at A, B, minus C. Other minus Q will be at this left side, which where the B is negative. So that means A minus B, C. And one minus Q will be towards the uh, inner side of towards the left side of the plane 3. So here the A is negative. So that means A minus A, B and C. So minus Q we have already calculated. To find out the plus Q, what you need to see. So we know that the total potential should be 0, right? Because these are grounded. So these two are already cancelling. So to cancel the minus Q charge, you just, because it is minus Q, so you just put the plus Q at the other, uh, the negative part of the coordinate. Like if it is A, B minus C, put it minus C minus B, C. Similarly, put plus Q at minus C, and this is B, this is minus C, and put it like A minus B minus C. So we know, now you know the coordinate, right? So you know the coordinate of all the 7 charges. So to find out the potential, V is nothing but V at any point XYZ, it is KQ by R, right? So K 1 by 4 pi epsilon naught. So QABC will give Q by square root X minus A square, Y minus b square plus z minus c. Similarly, for minus a minus b c, this will become x plus a, y plus b, and z minus c. So I think you can uh, calculate the potential now. Or you have any doubt? Do you have the doubt? Let me know, or I will try to clarify it, or we'll move to the next problem. Okay, so let us move to our next problem. So there is a charge. Also, it is similar to what we've seen in question number 3. But here we need to calculate what is the force on charge Q, what is the potential, and what is the surface charge density. So instead of a parallelepiped, we have only two planes which is intersecting at an angle 90 degree. So these are infinite conducting plane, grounded conducting plane. So these are grounded. This is also grounded. Uh, one is at x equal to 0, y greater than equal to 0, which is this plane, and one is at y equal to 0 and x greater than equal to 0, which is this plane. For this configuration, calculate the charge. So there is a charge Q which is at a distance d1, d2 above two orthogonal grounded conducting plane. So Q is there and d1 is the distance from x equal to 0 plane. That means this is d1 and this is d2. So number of image charges will be 360 y90 minus 1, which is 3. So the location of charges, let us see. So let me remove it so that I can show the image charges. So one will be minus q at d2 distance here, and one will be minus q at d1 distance, and one charges will be here, which is plus q at a distance 2d2. So these charges should be present so that the total potential on any of this plane should be 0. So here you can consider one plane. Let us say this plane. So the total potential for this charge and this charge is 0. But for this charge, it is for this image charge, it's not 0, right? So to make it 0, we are placing a image charge symmetrically for this plane here, so that the total potential is 0. Yes, sorry for the typo, it is 2d1. Okay, so to make the total potential 0 here, we are placing a plus q charge. So this is why we have three charges. It's not like we have minus q here and minus q here. It's wrong, because for that case, the total potential will not vanish. So you have to put a plus q charge so that total potential is 0. So to find out the force, it's now easy because you know the coordinates of all these image charges. Force will be, let us say, this will give a force, attractive force F1. This will be F2, and this is F3. Okay, so this won't be attractive, right? So this is a repulsive force. So that means this is in this direction. Total force on charge Q is due to the total force due to other charges F2, F3, F2, F3, and F1. So F1 is force between these two charges. Distance is 2d1. So this is 1 by 4 pi epsilon naught q square by 2d1 square. Direction is this is xy plane, right? So it is minus jk. Similarly, F2 force between these two distance is 2d2. 1 by 4 pi epsilon naught q square by 2 d2 square minus ik. Now let us calculate F3, force between 3. So F3, let us say this is 1 by 4 pi epsilon naught q square r square by rk. So r vector is, it's the position vector, right? So it is at a distance 2d1 and this distance is 2d2. I hope you are not confused by the diagram. So this is r vector, right? So this is at a distance 2d1 and this is 2d2. So 2d1 ik plus 2d2 jk. So r cap you can find out, this will be r by mod r. So you will give, let us say this is angle theta. So you will get this is cos theta I cap plus sin theta jk. Cos theta is 2d1 by mod r. So this will give cos theta is 2d1 by square root 2d1 square plus 2d2 square. Sin theta is 2d2 by mod r, which is this is. So F3 is now 1 by 4 pi epsilon naught 1 by r square. R square will give 4 d1 square d2 square 2 d1 I cap 2 square root d1 square d2 square plus 2 d2 j cap 2 d1 square d2 square. 2 will cancel. So now we can calculate what will be F, which is F1, F2 plus F3. So let us take K is 1 by 4 pi epsilon naught. So we have K Q square 4 D1 square minus IK plus K Q square 4 D2 square minus JK plus K by 4 D1 square plus D2 square D1 square root D1 square plus D2 square I cap plus D2 JK square root D1 square plus D2 square. So this will be the total force on charge Q due to the other charges, which is mostly the image charges. Only the image charges is there, so that is why we are considering the image charge force. First term is okay. I have written F1 here. This is F2 and this is F3. So I hope force is clear. Let us calculate what will be the potential. So its potential is easy because you know the coordinates. But let us calculate so that we can calculate the answer for the next question. So let us see the coordinates for. So Q is at D1, D2. Other charge is present. This is Q, D1, D2, right? Or yes, D1, D2. Other charge minus Q is at minus D1, D2. One charge is there minus Q at minus, sorry, this should be D1 and minus D2, and plus Q charge is at minus D1 minus D2. So V, X, Y, you can take Z also, doesn't matter. This is K, Q for this one, K, Q, Y, R, which is X minus D1 square plus Y minus D2 square. For this, it is minus KQ square root X plus D1 square Y minus D2 square. This one is minus KQ square root X minus D1 square Y plus D2 square, and last is KQ square root X plus D1 square plus Y plus D2 square. This is the potential. So if you know the potential, calculating the surface charge density is easy. So because here, if you see the figure, you have two planes, two grounded conducting planes. So that means there will be induced charge here and there will be induced charge here. So there will be two surface charge density that you need to calculate. So let us calculate for the plane, conducting plane. For x where x is 0 or y greater than 0. That means this plane, this perpendicular plane. So for this, we have sigma is minus epsilon naught dou b by dou n, and the normal vector to this plane is dou v by dou x, where x is 0. So we just need to take a derivative of v and put x equal to 0. Don't put x equal to 0 in the potential directly because it will give a wrong value. So first take the derivative, then only after the derivative put the value of 0. So sigma is minus epsilon naught aq. So first we'll give minus x minus d1. So there will be a 2, but the 2 will cancel with the 2 that will take from, so there is a half here, right? So this will give a 2 and the square will give a 2. So they will cancel. Cube root minus d1 square y minus d2 square. So 1 z square was missing here. Okay, so for the second case, we have, there is a negative here, so it will be plus x plus d1 cube root x plus d1 square y minus d2 square plus z square. Similarly, here it is negative, so plus x minus d1 cube root x minus d1 square y plus d2 square plus z square. And there is a plus will give minus x plus d1 cube root x plus d1 square plus y plus d2 square plus z square. Now we can put x equal to 0. So sigma will be minus epsilon naught kq d1 cube root d1 square plus y minus d2 square plus z square d1 cube root d1 square y minus d2 square plus z square minus d1 cube root d1 square plus y plus d2 square plus z square, and last one is minus d1 cube root d1 square z square plus y plus d2 square. So the total will be, so this will add up, this two will add up. So finally you will get minus q d by 2 pi 1 by q d1 d1 square y minus d2 square plus z square minus 1 by square root d1 square y plus d2 square plus z square. So this is for the one of the plane. For the next plane, which is this one, here it is y is 0 but x is greater than equal to 0. So for this, sigma would be minus epsilon naught. The normal vector is 2v by dou y at y equal to 0. So let me quickly do it. So vxy, we have, we take this sigma would be minus epsilon naught kq y minus d2 cube root x minus d1 square z square y minus d2 square y minus d2 square root, sorry, cube root y plus d2 cube root x minus d1 square y plus d2 square plus z square, and lastly we have y d2 cube root x plus d1 square plus y plus d2 square plus z square. So put the value of y equal to 0 here. So let me write the final sigma you will get. Finally, you will get q d2 by 2 pi 1 by square root x minus d1 square z square plus d2 square minus 1 by square root x plus d1 square d2 square plus z square. Okay, so this is for another plane. Do the intermediate step, we will get. Okay, so for now, let us move to our next problem. So there is a system of two circular coils carrying equal currents I along the same direction, having equal radius r, and these are separated by a distance r. So there are two coils. Let's say it is carrying current I in the same direction. Radius is r, and these are separated by a distance r. Find the magnitude of the magnetic field at the midpoint P of the line joining the center of the coil. So I hope you know the formula for this. Do it and let me know the answer. Okay, if it is taking time, let me do it quickly. So, recall the formula is B at point P is mu naught I r square by 2 r square plus d squared 3 by 2. So d is the distance from the observation point to the center of the coil. So if you see the two coils, they are in same direction. So that means the field that they will produce here, they will add up. So if you see the field direction, so I think this will be this direction. So they will add up, and because they are in same distance and they have same radius, so that means the field value would be equal. So B1 B2 is equal, which is mu naught I r square 2 r square. D is r by 2 square over 3 by 2. That means the total field would be B is to B1, which is 2 mu naught I r square 2 r square by 4 3 by 2. 2 2 will cancel, so this will give uh, 8 mu naught I by 5 root 5 r. Yes, it's option A. Good that we have do the calculation. So this is like a Helmholtz coil. So similar to the Helmholtz oil problem. Okay. So let us move to our next problem. Next problem is also easy. Uh, it's based on a long wire. So first question is to find out what is the magnetic field at the center of a square loop of side 2R, which carries a steady current I. So this is easy. Uh, it's a square loop and it's given it is 2R and there is a current that is flowing and you need to find out the field at the center. So if you look at each finite wire, so they are producing the field in the same direction, right? So it's like it's in downward direction for this field. So and the distance is for the square loop, the distance is equal. So that means they all will add up and they are all equal. So that means B total will be 4 times B1 and 4 times B1 is mu naught I by 4 pi S sine theta 2 minus sine theta 1. So theta 2 and theta 1, because it's a square loop, theta 2 and theta 1 are 45. So this should be B total is 4 times mu naught. So this is mu naught I by pi S sine 45 plus sine 45. So 1 by root 2. So it will give root 2 mu naught I by pi S. S is R. This is for the square loop. Now, in the second part, it's a n-sided regular polygon. Regular means all sides are equal. So n-sided regular polygon carrying a steady current I, and R is the distance from the center of the polygon to the midpoint of any side. So you need to find out the field for this case. So this is also quite easy. You just need to find out what is the angle and what is the I think angle would be fine. So to find out the angle, so this because this is the n-sided polygon, so that means the angle made by each side, theta, should be pi by n, right? Sorry, 2 pi by n for each side. So this total angle should be 2 pi by n, and for this, because this line is joining between the center to the midpoint, so theta 2 would be pi by n and theta 1 should be minus pi by n. Okay, so now we can calculate the B total, which is n times B of B1. N mu naught I by 4 pi r sine pi by n plus sine pi by n. So this is mu naught n I 4 pi r to sine pi by n pi by n. This is the total magnetic field. Okay. So in the next problem, what we have, there is a charge q which enters a region of uniform magnetic field, which is out of the base and in the z direction, with an initial velocity in the x direction. So it's given b is in the z direction, some b0 kk, and initial velocity is in the x direction. The particle is deflected a distance y above the initial direction. If the region has a width x, you need to find out what is the sign of this charge and what is the deflected distance y as a function of q, v, and x. So there is charge q moving with initial velocity v, and there is a outward v, and the region where the v is present is x. And while traveling through this region, it is deflected by a distance y. So you can say v cross b would be in, what would be b cross b? The direction would be in I cap cross k cap, which is minus j cap, right? But it is moving along the positive y direction. That means the q should be negative. So it's a negative charge so that it can deflect along the y direction. First part is fine. To find out the y, first we need to see how the particle will travel through this magnetic field. So if you see the x direction, there is no magnetic field, right? And it's traveling at a velocity v0. So that means if the distance traveled, which is x, it should be v into t. T is the time. So that means time, you can write it as x by v. For the y direction, the force acting is the magnetic force. So that means force MA is QVB sin theta, and theta is 90 degree. So that means the acceleration is along y is QVB by M. So y would be now v initial velocity along y dt plus half AOY t square. So this is 0 because initially it is along the x direction, the velocity. So that means this will be half AY is Q BB by M. T is x by v square. So that means you have Q B x square by 2 MB. MB you can write it as a momentum. So this is linear momentum. So this is QB square 2P. Okay. For the ninth question, it's quite similar to the eighth question, but here the path is quite different. So here you can see a proton is shot at speed 10 to the 6 meter per second, along a line at an angle 30 degree to the x-axis. So it is projected at an angle 30 degree to the x-axis, and v is given 10 to the 6 meter per second, parallel to which a uniform magnetic field is given, it is present. So B is along this direction, it is 0.2 Weber per meter square. Describe the motion of the rotor. So for this case, the velocity, it is two component, one is parallel and one is perpendicular. So parallel is parallel to the magnetic field, which is V0 cos 30 I cap, and perpendicular is V0 sin 30 J cap. So parallel component, it won't experience any force. So that is why Vx, which is V parallel, it will remains constant. The velocity in this direction will remain unaffected. But because of this perpendicular component of this velocity, there will be a force along the, which direction will be? It is j cap and this is I cap. So this would be in the minus k cap direction. So that means the motion would be a helical trajectory. So it will move like this. So it is moving along this direction due to the parallel component, and it is making a circle because of the perpendicular component. So that is why it should be a helical path. Okay. And if you want to find out what will be the radius of this helical path, uh, this you can write it by equating the centripetal force, which is mb square by r is qbb. So that means this perpendicular r is mb by qb. And if we put the value of mass of proton, p perpendicular, q and b, we will get the radius will come out around 2.6 centimeter. Okay, so this is radius, and another important component is the pitch. Pitch is, it's a distance travel over one complete rotation. So like this distance for one complete rotation, what is the distance travel? So this is equal to V parallel into T. T is the time period, which is 2 pi r by V perpendicular. So if you put the values, this will come around 28.3 centimeter. Check it if you have any, if you are getting any other solution, let me know. Okay, so let us see our next problem. For the next problem, we have one infinitely long, thin metallic stripe of width A. So there is a stripe of width A, carries current I in the I, which is uniformly spread over its plane. For this case, you need to find out what will be the magnetic field at a point in the plane at a distance x from the nearer edge. So let us say this is the nearer edge. You need to find out what will be the magnetic field at the point P. For this stripe, which is width A. So to solve it, what you can do? So you can think that this stripe, it is made up of a series of long thin wires. So you know the magnetic field for the thin wires, which is mu naught I by 4 pi s sin theta 2 by sin theta 1. Sorry, sin theta 2 minus sin theta 1. So if you see, if you do, if you imagine that this is made up of a infinity number of long wires, and if you find out the magnetic field for one of this wire and take the integration, then you will get the magnetic field for this whole stripe. So let us do it. For this, we need to take a wire element. Let us say this is at a distance y from the point. So this is dy. So that means this point is y is x. This is y is x plus a. For a infinitely long wire, what is the magnetic field? Bp will be mu naught by 2 pi y, right? So, so dBp, which is the field due to this infinitely small element. So this is mu naught di by 2 pi y. And it's given that the I is distributed uniformly over this stripe. So you can write di is I by a into dy. So that means dBp is mu naught by 2 pi y I by a dy. So now we just need to take the integration of dBp, which is this is mu naught I by 2 pi dy by y. Limit would be from x to x plus a. This integration is easy. Dy by y is ln y, so 2 pi ln x plus a by x. But you can further simplify it. You can see that it's given it's a thin metallic stripe. So that means a is much less than x. So for this, you can do an approximation. So you can do ln x plus a by x. This is ln 1 plus a by x, which is x when a is much less than a. So BP would be mu naught I by 2 pi a by x. A will cancel. So we have mu naught I by 2 pi x. Okay. You mean this one? It's based on a trick that you take the stripe as a series of thin wires, and then you find out the field for one of the thin wire, then you integrate it over the whole width of this stripe. So can I move to the next question? Okay. So there is a charged particle in a uniform magnetic field. B is d0 kk. It starts moving from the origin with velocity. Velocity is given. V is 2ik plus 3kk. So you need to find out what is the time at which it reaches a distance 6 meter above the xy plane. So this is quite easy. Just use the concept that we have used in one of our previous problem, and let me know the answer. So there are four options. Option is 1 second, option B is 2 second, option C is 3 second, and option D is 4 second. Anyone? So it's saying what is the time at which it reaches 6 meter above the plane, XY plane, right? And you can see there are two components. One is parallel to the magnetic field, one is perpendicular to the magnetic field. So the parallel component, it won't experience any force because there is also no electric field is there. So that is why force is zero. That means acceleration is zero, and the velocity will remain constant in this direction. But because of this perpendicular component, will have helical path, circular path, and when it combines with V parallel, will have helical path. So the time it is so to move it from a plane to 6 meter above the plane. So this is x should be v parallel into t because only v parallel acceleration is zero. So you can directly relate the position with the parallel component. So that means time would be x by v parallel, or let us say this is d. D by v parallel. D is given, this is 6. V parallel is also given 2. So this is 3 seconds. So answer would be option, sorry, V parallel is 3, right? So answer would be option 2, option B. Is it clear? Okay. So the velocity has two components, right? One is V parallel and V perpendicular. So whenever it tries to enter this magnetic field, so there will be a helical path, right? Because it is, and this motion is due to the V parallel component, and this motion is due to the circular one, it is due to the magnetic force, V perpendicular. Now, if we look at, we know the general relation between the position, time, and acceleration, right? The general formula is distance is the initial velocity a t square. This is the formula that we use again and again. But if you see the V parallel component, which makes the charge particle move in the perpendicular direction, so there is no force in this direction. So that is why the velocity in this direction will remain unchanged. That is why velocity is constant, so acceleration is zero. So so that means, and it is also given it is moving at a distance 6 meters above the xy plane. XY plane is the plane where the circular movement is happening, circular motion is happening. So S is given, this is 6. V parallel is, it's also given, it is 3. Time we need to find out. So time will be 2 seconds. Okay. So let us see our next problem. So there is a point charge Q located at 102 between two infinite conducting plates. These are infinite conducting, semi-infinite conducting plane intersecting at right angle. So there is a charge Q which is 102. Determine the potential at a point P303. This is somewhat related to one of our previous problem, but for that case we have written only the general expression. But for this case we need to calculate the exact value of the potential. So image charge. Okay, so this is capital Q. So there will be minus Q at 1, 0, minus 2, and there will be Q at minus 1, 0, minus 2, and mm, minus Q at. So we are considering the xz plane. Don't confuse with the xy plane. So this would be minus 1, 0, 2. Yes. So this is the distance d1. This is say this is d2. This is d3. So potential at the point P that we want to calculate is Q by 4 pi epsilon naught 1 by R1. Let us denote the point by some letter. This is B point. This is C point. This is R point. This one, let us say this is A point. So 1 by R1 minus 1 by R2, 1 by R3 minus 1 by R4. So R1 is nothing but the distance between P and R. So this point we are considering. So PR would be, P is given, it is 303, sorry, 303. And R is also, we know it is 102. That means PR would be 3 minus 1 square plus 3 minus 2 square. It would be root 5. So R2 is PB. B is this point minus 102. So that is why this should be minus 1. So this is 3 plus 1 square. 3 minus 2 square, which will give root 17. R3, it is PC. C is, I think, minus 1 minus 2. So this is 3 plus 1 square plus 3 plus 2 square, which will be root 41. And R4 is P, which is 3 minus 1 square, 3 plus 2 square. This will be square root 29. So potential at 303 is Q by 4 pi epsilon naught, 1 by root 5, 1 by root 17, 1 by root 41, minus 1 by root 29. And if you simplify it, this approximately gives a value of 0.19 Q by 4 pi epsilon. So answer would be option D. Okay, let us see our next problem. It's based on the Ampere's law. So there is a steady current I which flows along the length of a long cylindrical wire of radius R. So there is a long cylinder of radius R. Find the magnetic field inside and outside the cylinder if the current is uniformly distributed over the outside surface. So current is only at the outside surface. So that means if you consider a region R less than R, there will be no I enclosed. I enclosed should be 0. So that means when you use the Ampere's law, it is 0. So B is 0 inside. For outside one, sorry, for R greater than R. So because it's a long cylindrical wire, so that means you can directly use the formula for the long wire. So that means B is long infinity wire, which is mu naught I by 2 pi R. Or you can you can take Ampere's loop. So remember that for a wire, the field is in the direction of the circumference. So that is why we are taking a Ampere loop like this. Okay. So this for this B is in the phi cap direction and mu. So B dl. So B phi cap dl is r dr d phi, right? No, it is d phi only. r d phi phi cap. So this is equal to mu naught. Total current is I in the outside surface. So this will give B 2 pi r, which is mu naught I. So which will give the same answer like before. So mu naught I by 2 pi r. So this is for the case where we have current in the outside surface. In the second case, the current is distributed such that J is proportional to R. R is the distance from the axis. So it's for B part, it's given J is CR, some constant CR. So that means if you want to find out the total current is J dA perpendicular. And remember, dA that we're considering is, so J is in this direction, so dA should be the area element of this surface. So J is CR and dr is r dr d phi. So for the total current is I is given. So if you put it, phi limit is from 0 to 2 pi, r is from 0 to capital R, C r square d phi d. This is 2 pi c r cube by 3. So that means the value for this constant is 3I by 2 pi r cube. So J is 3I by 2 pi r cube r. So let us see for the inside one. For r less than r, you can consider this is ampere loop at a distance r. So first let us see what will be the total I enclosed, which is JD. R is 0 to R, pi is 0 to 2 pi. So this will give 3I by 2 pi r cube d phi integration and dr, which is r square dr from 0 to r. So this is 3I by 2 pi r cube, 2 pi r cube by 3, which is I r cube by capital R cube. So we know the I enclosed. So BDL should be mu naught I r cube by capital R cube. So B would be mu naught 2 pi 1 R from here will cancel with R cube. So this will give I R square by R cube. Direction is pike. This is for the inside one. For the outside, when R is greater than R, the total I enclosed will be I, right? So that means the B would be the same as the before, mu naught I by 2 pi r cycle. So is this problem clear to you? Okay, question number 14. It's similar to what we have seen before. So let me skip it. Uh, please solve it and let me know whether you are getting the right answer or not. Okay, so for this question, the answer would be option B. So there are there is a charge q at a distance d from two perpendicular planes. So you need to find out the force experienced by this charge in terms of the unit 1 by 4 pi epsilon naught. Do it, solve it, and check whether you are getting the answer B or not. Okay. So for now, let us move to our next problem. There is a wire with uniform line charge density lambda per unit length carries a current I as shown in this figure. And you can take epsilon naught mu naught as 1. And for this, a particle of charge q is at a distance r and is traveling along a trajectory parallel to the wire. So what is the speed of this charge? Option A is lambda by I, option C is lambda by 3I, then lambda by 2I, and 4 lambda by I. So how we can solve it? So one clue is given that the particle is moving in this direction. Okay. So if you know well, what is the force that the particle will experience here? So because of this long wire, there will be there will be a magnetic field that will be created at a distance r, and the direction would be it is pointing toward into the page. Okay, so there will be a magnetic field B, and because of the magnetic field, the particle will experience a force. And what is the direction of this force? So V cross B, right? V is in the upward direction and B is pointing into the base. So V cross B. So that means it is towards the y. So force is in this direction for the magnetic field. And it's also given this wire is charge density lambda. And because of the charge density, we'll see a electric field at the same point, and the direction of the electric field would be in this direction, right? So because of this electric field, it will experience a electric force, which is F electric. And it's given that the particle is moving in the upward direction. So that means these forces are balancing with each other. That is why the particle is not attracted to this wire, or it is not getting repelled by this wire. So it is moving unaffected parallel to this wire. So that means we have to equate magnetic force and electric force to find out what is the speed of this charge. So F magnetic, it should be equal to F electric. Okay. So to find out electric force, we need the electric field. And electric field due to a long wire, if you recall, it is lambda by 2 pi epsilon naught r. This you can easily get it using the Gauss law. And the direction is RK. And so that means electric force is QER. Magnetic force, it is QVB. It is Q B cross BR. So that means it is QVVR. Let us equate it. So QER is QEBR. So B is ER by BR. ER we know it is lambda by 2 pi epsilon naught, and BR due to a magnetic field, if we recall, it is mu naught I by 2 pi R. So that means this is lambda by 2 pi epsilon r, and this is mu naught I by 2 pi r. So we can take mu naught epsilon as 1 because it's given in the question. So answer would be it is lambda by I. So velocity, it is related to the linear charge density and the current flowing through it. Answer would be option A. Is it clear? Okay, so let us move to our next problem. So there is a loop shown in this figure. Below carries a steady current I, the magnitude of the magnetic field at a point O. So you are given a loop like this. The current is flowing in. That means this will be in this direction. I. This is A. This is 3. So to find out the magnetic field, you need to see the contribution from each of these elements. So there are two straight wires, A, B, and there are two semicircle loops, C, and outside is D. So that means the B at O would be B due to A, B, C, and D. But if you look at AB, this is along the line where O is present. Okay. And for a wire, if you recall, the B is mu naught I by 4 pi S sine theta 2 minus sine theta 1. So if the angle is 0, so if it is along the same line, so this angle is 0, that means there will be no magnetic field. So BA and BB, it is 0. Now for the CD, it is half circle. Okay. But we know the field due to a full circle. So that means B due to a semicircle. It would be half of this B due to the full circle, which is mu naught I r square by 2 r square plus z square 3 by 2. Z is 0. So this will give mu naught I r square by 4 r cube, which is mu naught I by 4r. So that means B A, it is mu naught I by 4A, and this is pointing out to the page, and B3 is mu naught I by 4 3A, and it is pointing into the page. So the total would be mu naught I by 4A 1 minus 1 by 3. So it would be mu naught I by 6, I think. 6A. Option B. Okay, for the 17th question, there are 2 point charges plus 3q and minus q. These are placed at 00D and 002D. So let me draw it. So there is a plane conducting it, and there are two charges which are placed at this is plus 3q at d distance. This is minus q at 2D. This is Z, X, Y. So for this, you need to calculate what will be the potential at a point 0, 0, Z, where Z is much, much greater than D. So find out the electrostatic potential at a point where Z is much, much greater than D. So there are two concepts here. One is the image charge and one is the multiple expansion. So there is a conducting plane, so that means you can, to simplify the solution, you can use the image charge. So there will be minus 3q charge at a distance d, and there will be a plus q charge at a distance 2d from the plane. This is the image charge. Now we can use the multiple expansion because the point where we are observing is much, much greater than d. So let us calculate the monopole first. Monopole moment. This is nothing but the summation of all charges. So if you sum it up, this will give a 0. That means the monopole term is not dominating. Let us see the dipole term. Dipole moment. So dipole moment, it is given by summation of Ri prime and Qi, I from 1 to 4. So for 3q, distance is dkk. For q minus q, it is 2qd kk. For minus 3q, it is plus 3q dkk. And for q, it is minus q, actually minus 2dq kk. So this is 2qdkk. So dipole term is not 0. That means the dominant term for the electrostatic potential for a large distance is dipole term. So V for ZZ greater than D will be dominated by V dipole. And if you recall the dipole formula, it is 1 by 4 pi epsilon naught P dot RK by R squared. This is P, R is ZZK, RK should be KK. So 1 by 4 pi epsilon naught 2QD KK dot KK divided by Z square. 1 by 4 pi epsilon naught 2QD by Z square. So answer will be option B. Okay. So let me ask whether you have any doubt in any of this problem. Okay, so let us see our next problem then. So there is a charged particle. It is at a distance d from the infinite conducting plane maintained at zero potential. Rotation is related distance d. When released from rest, the particle reaches a speed u at a distance d by 2. So when it comes to d by 2, the speed is u from the plane. So the question is asking at what distance from the plane will the particle reach the speed of 2u. So we need to see at what distance U becomes 2U. So it's what is the force that is experienced by this particle? Q. It is because of this induced charge on the plane, right? Or you can say the image charge. The force is minus Q square by 4 pi epsilon naught 2D square. So this is Q square by 16 pi epsilon naught D square. So this is for a distance D, you will see a force this. But for a general distance, if you consider, let us say it is at a distance x. So force will be Q square by 16 pi epsilon naught x square. And force you can write it as m dv by dt, right? Which is Q square 16 pi epsilon naught x square. So let us take m to this side. And let us take this is as a constant other than the negative sign. Let us say this is c by x square. So to solve it, to find out the relation between v and x, what you can do, let us multiply v in both sides. So v is also dx by dt. So v dv by dt, it is nothing but the derivative of time derivative of v square, and 1 by x square is the derivative of d by dt of minus 1 by x. So that means this is the derivative of c by x. So this means v square by 2 is c by x plus some constant d, that we can get it from the boundary condition. So it's given that at x equal to d, it is released. That means the initial velocity is 0. So v is 0. So if you put it here, you will get d is minus c by d. So v squared by 2 is c 1 by x minus 1 by t. So this is the relation between the velocity and the distance of the particle from the plane. Okay, so to find out the distance at which it will reach a velocity to you, what you can do, you just take the ratio v1 by v2 square. It should be 1 by x2 minus 1 by d, 1 by x1 minus 1 by d. Question is, okay, so this is the question. Let me know when are you done. Okay, so one case is given that when v1 is u, the distance x1 is d by 2. Otherwise, v2 is 2u, but you don't know what is x2. That we get it from here. So this is 2u by u square 1 by x2 minus 1 by d 1 by x1, which is 2 by d minus 1 by d. So this will give 4 by d, which is equal to 1 by x2, 1 by d. So this will give x2 is d by 5. So when it reaches d by 5 from the plane, the velocity would be twice of u. Okay. Okay, so let me move to our next problem. For 19th question, there is a charged particle which moves in a helical path under the influence of a constant magnetic field. The initial velocity is such that the component along the magnetic field, that is V parallel, is twice of the component in the plane normal to the magnetic field, V perpendicular. The ratio L by R, where L is the pitch and R is the radius of this helical path. So we need to find out what is the pitch to the radius ratio. So this is directly based on the formula. So pitch is nothing but V parallel into time period R. V parallel is, sorry, T is 2 pi R by V perpendicular. So that means RR will cancel and 2 pi V parallel by V perpendicular. So this ratio is given, it's 2. So that means answer would be 4 pi. Option C. Okay, let me see whether 20th question. Let us solve 21 first because it's quite straightforward. Then if we have time, then we'll solve the 20th question. Can you let me know the answer for this question? So there is a point charge Q which is placed at 0, 0 d above a grounded infinity conducting plane defined by z equal to 0. There are no charges present anywhere else. What is the magnitude of the electric field at 0, 0d? Yes, the previous answer is 4 pi. Can you let me know the answer for this? It's quite straightforward. it's not option A. So let us check. So to find out the electric field, so if you know the one thing you can do is find out the potential, then take the derivative of it. Other thing is what you can do is if you know the force, then finding out the electric field is quite easy. So force is for this configuration, there will be one image charge, Q, and there will be minus Q. And the distance between them is 2D, right? So force will be minus Q square by 4 pi epsilon naught 2D square. So that means electric field is minus Q. 4 square will give 2 square will give 4. So this is 16 pi epsilon naught D square. Option D. Okay. So 20th question it will take some time. So we'll see it in our next live session. So let me ask whether you have any doubt in any of this problem. Otherwise, we'll stop for today. Dinakar, do you have any other doubt? Okay, so thank you for joining the session. I hope the problems it will be helpful for you to solve the assignment as well as it will be helpful for uh, numerical solving the electrodynamics questions or clarifying your concept. So we'll meet on next Friday for same time from 6 to 8. We'll solve few more problems related to the contents of week 10. So let us stop for today. Let us meet on next Friday. Thank you, everyone.